Welcome to the 7th video on linear algebra. In this video I will cover the topic of diagonalizability. Before we can talk about diagonalizability, we will talk a bit about similarity, which is a more general notion. So, and it's important to keep in mind that it might seem a bit strange, these notions that we're defining now, but the motivation by diagonalizability lies in the application in the next section, which is systems of linear differential equations. So for now, we just have to accept these definitions as they are, and later we will see why they are interesting. So let A and B be square matrices of the same size. We say that A is similar to B if there exists a non-singular matrix S that is of the same size, such that A can be decomposed in this way. So we have A is equal to SB S inverse, and we denote this by A sim B. What we can show about similar matrices is that they have the same eigenvalues, and this will be important when we look at diagonalizability. I will explain this in a little bit. So we now define diagonalizability. A square matrix A is said to be diagonalizable if there exists a diagonal matrix B such that A is similar to D. So basically what that means is A is diagonalizable if we can write A is X D X inverse, where this D now in particular has to be diagonal. So what that means is that the only non-zero entries in the matrix are on the diagonal. So everything is zero except on the diagonal where we have some non-zero entries. And basically why this property is important is that we can show that this matrix D will have the eigenvalues of A on its diagonal, so as the non-zero entries, and X is a matrix whose columns are eigenvectors of A. The way of showing this is a bit complicated, so I omit it here, but it is an important fact that we will need in our application that we will see later. So now we want to investigate for which matrices it holds that A is diagonalizable. So there exists this diagonal matrix D such that A is similar to it. To investigate this further, we first need to define the notion of linear independence. You might have also seen this in other lectures, but I will again cover it here just so we're all on the same page. So we have these k n vectors, and we say that they are linearly independent if this equation, so having some scalars times these n vectors and we sum them up and set it equal to 0, if having this expression be true implies that all of these scalars are 0. So in some sense there is no way in which you can add up these vectors so that they cancel each other out, so they are independent. If this is not true, then we say that these vectors are linearly dependent. So as an example, we have this vector and this vector, so the transposes of these two, and they are linearly independent because if we do C1 times this plus C2 times this, we get C1, C2 is 0, 0. This implies that C1 is 0 and C2 is 0. So then if we look at our definition, we say that these are linearly independent if this is 0, so this is 0, implies this is 0, which is exactly what we find. And yeah, so we then have this result. A square matrix is diagonalizable if and only if it has n linearly independent eigenvectors. So yeah, so if you look at all its eigenvectors and you multiply them by these scalars and you set it equal to 0, and you find that this implies that all of the scalars are 0, then the matrix is diagonalizable. And similarly, if the matrix is diagonalizable, it is true that taking its eigenvectors, multiplying by some scalars, immediately it follows that the scalars must be 0. So this gives a characterization of diagonalizability, and actually another characterization of diagonalizability. So it relies on this wordy result. So if A is an n by n matrix and k is some natural number which is less than or equal to n, and these lambda k are distinct eigenvalues of A, distinct, very important, and they have corresponding eigenvectors x1 up to xk, then x1 up to xk are linearly independent. So you can already see where this is going. On the previous slide we had that it is diagonalizable if and only if it has n linearly independent eigenvectors. So we see that if k is equal to n, then all the eigenvalues are distinct, and so all the eigenvectors are linearly independent, so the matrix is diagonalizable by the previous theorem. So yes, exactly. If k is n, then it follows that the matrix is diagonalizable. So every square matrix, every n by n square matrix with n distinct eigenvalues is diagonalizable. And we summarize that in this chart. So first we saw that A is diagonalizable if and only if it has n linearly independent eigenvectors. And that is implied by having n distinct eigenvectors. N distinct eigenvalues, sorry. Note, however, that this implication, this way, does not necessarily have to hold, because the eigenvectors can be independent, but there can still be non-distinct eigenvalues. It's only this implication that holds. Okay, now we look at some properties of diagonalizable matrices. So a nice property, which we will see is a desirable property in our application, that we will cover in the next video, is that if we raise a diagonalizable matrix to some power, we can decompose it into xd x inverse, where this is diagonal, and these are the matrices with, this matrix actually, only x, has the eigenvectors as its columns, and this x inverse is just the inverse of x. Then we can show that a to the k is xt to the k x to the minus 1, so it is very easy to raise a to some power. Of course, if you have a normal matrix that is not diagonalizable, to compute a to the k, you have to multiply a by itself k times, which is quite a hassle. And another nice thing about diagonalizable matrices, and diagonal matrices in particular, is if we take a diagonal matrix, let's say this one, let's call it D1, D2, so this is a diagonal matrix, and we raise this to the power k, then what you can show is that the only thing you need to do is to compute the right hand side is also raise these things to the power k, and then you are done. So it makes it very easy to compute the powers of a. So we can do a little proof by, sorry, there was some dust on my screen, proof by induction of this. So yeah, let's do this. So for our base case, we have, we have k is equal to 1. So then we have a is xd x inverse, and yeah, this is certainly true because yeah, a is diagonalizable. So then we take some k and n, and we assume that this holds for this k, and want to show it holds for k plus 1. So we have a to the k plus 1. We can write this as, yes, we can write this as a to the k times a. Then by our induction hypothesis, a to the k is equal to x to the, or x d to the k x inverse, and a is diagonalizable, so we can write x d x inverse. Then we cancel these two because they are identity, so we have x d to the k d x inverse. This d, these d's we can take together. We can just say that it's d to the k plus 1. And this is x inverse. And this is precisely what we wanted to show. So that concludes our little proof to QED. Okay, that concludes the section on diagonalizability. In the next section, we will cover an application that uses everything that we've discussed so far. And yeah, I hope you liked this video, and I'll see you in the next one.